but today he's going to talk about fully randomized benchmark. And, so he's around visiting all day. So definitely if you want to chat, he's available. And we also have lunch after this, thanks to us. So please stick around.
All right, well, thanks for the introduction. So I'm Alex, and I work at NIST in Boulder in the quantum theory group, which is led by Manny Knill and Scott Glancy. Today I'm talking about some work we've done on fully randomized benchmarking, and in collaboration with some of the members of the ion storage group at NIST in Boulder. So in particular, I'm talking about optimized experiment design and analysis for fully randomized benchmarking. Right, so I wanted to start by, I guess, giving some context for this work in terms of the other things that I'm interested in and our group is interested in. So I put a sort of short list. So one of the main things that we work on in NIST Boulder is quantum characterization. And you can think of this as trying to infer the quality of quantum operations, very often ones that occur in AMO experiments. And these quantum operations can be anything from quantum states, quantum measurements, or quantum gates. And very often for each of these things, there are different characterization methods that are useful for each particular task. So one characterization method that we spend a lot of time thinking about is randomized benchmarking, and in particular, fully randomized benchmarking. And that's the main focus of this presentation. And I'll talk in a few minutes in a lot more detail about what this is. And so as part of the motivation for thinking about this, one thing we're also interested in is understanding the performance of practical error correction. So what that means is that in near-term experiments that will perform error correction eventually, one question is, how can we figure out ahead of time whether these will do a good job at actually correcting errors, or what is the performance of these error correcting codes? And so a very active area of research is trying to figure out exactly what kind of characterization tasks we can run to answer this question. And so we think randomized benchmarking is one good method for this, and I'll talk about that a lot more in a few minutes. Right, so just to mention some of the other things that we're interested in, quantum transduction is also something I spent a lot of time thinking about. This you should think of as trying to generate entanglement between two very different quantum platforms. One thing that we spend a lot of time on is entanglement between optical systems and microwave systems. So this is very important for something like quantum networking, and then also may eventually play a role in quantum computation in terms of linking different quantum processors to each other. Right, so that's quantum transduction. Specifically, I've worked on doing theory work for experiments with electro-optical mechanical devices. This is like an all-Gaussian transduction scheme. But I've also spent time thinking about systems like quantum dots in surface acoustic wave cavities and how they can be used for transduction. And these are non-Gaussian schemes. So at the end, if there's time, I can answer questions about this. We also spend a lot of time in our group thinking about quantum optics. One way to say what this is about entangled states of light between two optical modes, for example. So this can be in terms of single photons being split between two parties. It can also be in terms of Gaussian entanglement, so things like two-mode squeezing. And so we're interested in experiments that can produce these things and how to characterize them and so on. Specifically, we're interested in things like entanglement swapping and distribution optically, and this also goes back to things like quantum networking and trying to make entanglement across remote parties. Right, so those are three pretty specific things. In general, in our group, we do a lot of theory work that's motivated by experimental collaborations. So what that means is that experiments will have specific things they're thinking about or specific goals, and then we talk to them and then decide what sort of theory projects to work on. And these can be pure theory projects, or they can involve actual experimental data, which is indeed the case for this project. Right, so that's a bit of background about what we do. So today I'm just going to be talking about fully randomized benchmarking as the particular topic of interest for now. Right, So in terms of that, here's an outline. So I'll start by giving an overview of randomized benchmarking. I'll explain what that is, why it's useful. I'll talk about the benefits of fully randomized benchmarking. Just to say what those are quickly, two of the main ones are reduced uncertainty in the inference for randomized benchmarking, and also these models of non-Markovian error that we've been recently interested in. So I'll introduce all this, then I'll talk about a very recent experimental implementation of fully randomized benchmarking that happened at NIST in Boulder. Right, so that's the outline. We should have plenty of time for questions during the presentation, so if you want to ask something, just go for it. Okay, so I'll get started with an overview of randomized benchmarking. This is a very common characterization task that's been around for a while. And a good place to start thinking about it is in terms of a circuit that looks like this. So in a randomized benchmarking trial, there's some kind of state preparation side. And then there's going to be a sequence of Clifford gates, which are the things labeled here. There are 4 of them, labeled C1 through C4. And the lambda there denotes an error channel that is attached to this perfect Clifford gate, which is really what we're trying to characterize. So there's that, there's a random sequence, and at the end, there's measurement O. And collectively, that is a randomized benchmarking trial. So the way you construct these sequences is that you draw Clifford gates uniformly at random from the Clifford group. The Clifford group is a very popular gate set to try to characterize that consists of major axis pi/2 pulses on single qubits, and then also C naught across every pair of qubits. So together, those things generate the Clifford group. And then in randomized benchmarking, it's the Clifford group that we're often interested in characterizing. So that's how you construct these sequences. You draw a list of random Cliffords. This list here is only of length 4, but in general, it can be of very long lengths. So you generate your random sequence, then you have this state preparation, and then a measurement. And so the point of this measurement O is that you should think of it as determining either success or fail for this particular trial. So what that means is that effectively you have a 2-outcome POBM measurement at the end of the day. One of the labels is success, which you can think of as there are no errors that happened during this particular trial. The other outcome is fail, and you can think of that as there was some error during the trial. And then fail really is just that you did not get the outcome for the measurement O that you would have expected if the sequence was perfect and there were no errors. So that's really what success is getting the expected outcome. So the point of doing this and the point of running these random sequences is that the error channels lambda that I said are attached to each of these Clifford gates. The point of the randomization is that these error channels get twirled to effective depolarizing channels. I'll talk about this in a few minutes. What that means is that mathematically you can treat the error channels here, whatever they may be, just as depolarizing channels of some parameter. And what's nice about depolarizing channels is that the single parameter that characterizes them is really just the fidelity of the channel. So the point of this is that in general, the error channel lambda can be very complicated. On many qubits, there's a very large space of possible error channels. But if you have randomization like this, then it really simplifies the effective description of the channels. And it lets you infer just a single parameter to learn the fidelity of what lambda was. Right, so that's kind of the big picture of randomized benchmarking. In practice, the way this works is that you want to run these trials at many different sequence lengths. So here the sequence length is 4, but in general, you want to pick a bunch of different sequence lengths in an experiment to run. And then you perform these trials at each of those sequence lengths. You look at the statistics of success versus fail at each of the sequence lengths that you attempted. And then you look for the functional form of that success probability over sequence length. And so under standard assumptions that you make in order to easily analyze randomized benchmarking, you'll find that the success probability decays exponentially as a function of sequence length. And the goal of the experiment is really to infer the rate of that exponential decay. When you do that, you interpret it as the average fidelity of a Clifford step coming from the Clifford group that an experiment can actually perform. Right, so that's, like I said, is the big picture for randomized benchmarking.
Quick
Yeah.
question.
Yeah.
So here, assuming you only have one lambda for every single buffer.
Yes, exactly. Right, so like I said, that is an assumption that people make to simplify the analysis. If you assume that there is the same error channel lambda for every random clipper, that it's really easy to analyze how randomized benchmarking works. The thing is, in most experiments, this is not quite true. And you would expect to have a different error channel lambda for each of your gates that you can apply. So people have done a lot of work to study randomized benchmarking in this case, and they find that to a very good approximation, you still get an exponential decay, which you can interpret as the average quality of these clipper gates. Yeah, so that's definitely a very important subtlety. So people did really worry about this for a while. And they find that it does not provide a serious disruption. This kind of code. Yeah, thanks. Okay, so I thought it'd be important to say a few words about when practically do we care about using randomized benchmarking, or when is randomized benchmarking especially useful. So what I have to say about that is one important situation that comes up is when state preparation and measurement errors are large, and you want to characterize an error channel that is comparatively very good. And then the point of using randomized benchmarking in this case is that you can apply these log sequences of gates, which lets you get a lot more signal about the error channel that you want to characterize per each time that you have a state preparation and a measurement. So for something like tomography, which is another very common characterization method, that involves just applying the gate and the error channel once. So you have state preparation, the gate, and then measurement. So there are the same number of gates as there are state preparation and measurement. So if you have large errors for state preparation and measurement, that can sort of swamp out the signal that you're looking for in terms of the quality of the gate. And that can make inference pretty difficult. Yeah, so if that is the case, and this is the case in a lot of experiments, against trap-blind experiments especially, then something like randomized benchmarking is very useful because it allows you to apply these long gate sequences without worrying too much about what the actual state preparation and measurement errors are. So that's one way this is pretty useful. I would say another situation when randomized benchmarking is especially useful is to characterize clipper gates themselves. And so this kind of goes back to how we expect quantum computation to be eventually done. So one way that seems pretty plausible so far is that computation will be done with long sequences of clipper gates, and then also magic states injection to perform arbitrary gates ultimately. But in practice, the actual long sequences that you apply are going to be clipper gates, and then the magic states will be just prepared on the side. So from that perspective, it makes a lot of sense to sort of characterize your clipper gates in long sequences. And I think people really do expect that the quality of the clipper gates tells you a lot about the quality of any kind of eventual computation that gets done. Another reason that it's pretty important to focus on characterizing clipper gates is that in error-corrected codes, a lot of the codes people think about, especially the stabilizer codes, there the logical clipper gates are often transversal, which means that they can be implemented in a much more straightforward way, basically, compared to arbitrary gates. So as things go forward and people start to characterize the quality of logical operations in error-correcting codes, characterizing clipper gates is going to be around for a while. Right. So those are two things. Two more things where randomized benchmarking is especially useful. One is, sorry, it needs a second to load. Yeah. One is to simplify the expected system behavior. So this is kind of a really important thing that we think about. I was talking about the exponential decay of success probability that you get in the simplest situations. This is really nice because you expect exponential decay over a broad range of experimental circumstances. What that means is that any deviations from exponential decay indicate that something else is going on. In the case of randomized benchmarking, deviations indicate some kind of non-Markovian behavior. And I'll talk about this in the future in relation to the experiments that we've been studying. But this is very important, I guess, because in principle, the different types of non-Markovianity you could have in an experiment is extremely large. And so it's very hard to know where to start in terms of characterizing that. And so simplifying the behavior in the Markovian case is extremely important so that you can actually have a hope of detecting deviations from that. Right, and a main motivation for studying non-Markovianity is to answer this question, which is, I would say, a kind of important issue right now. And the question is, will non-Markovianity be a problem for future error correction? And so this is still pretty uncertain. I think most people believe that it's ultimately not going to be a problem and that our error correction schemes will handle this okay. But no one's really been able to come up with some kind of convincing argument or experiment that really demonstrates this yet. So going forward, I think this is going to be a pretty active issue. Right, so all of this is to motivate why we think randomized benchmarking is very useful and why we've spent some time thinking about it. Right, so there's that. I also wanted to say a few words about how randomized benchmarking works. So I mentioned the twirling of error channels before. So here are a few more details about this. And people have come up with many different ways of thinking about this particular issue. So randomized benchmarking twirling, you should think of it like this in equation 1. So you have that error channel lambda that I was talking about previously. So if you conjugate that channel with random Cliffords, what that means is you compose a Clifford before the channel with the inverse Clifford gate afterward. This is really what twirling is. If you sum over all the Cliffords like this, or equivalently pick a random Clifford to conjugate by. That is how twirling works in practice. You can show that if you apply these random sequences of Clifford gates with error channels following them, like in the diagram in the previous slides. What you have in equation 1 is effectively the situation you're interested in. And you can show that if you do this, the only remaining Krauss operators for the error channel lambda are going to be Pauli operators, like PJ, and they're going to be evenly weighted. So what that means is that the form of the channel in Krauss form is going to look, after twirling, something like equation 2. So in equation 2, this is basically the form of the depolarizing channel. So with some probability, nothing happens to your state. And then with 1 minus that probability, then you are conjugated by a random Pauli. So that's like a random Pauli error occurs. Yeah. So this is exactly what a depolarizing channel is. The parameter there is lowercase lambda. And you can show that the twirling that I'm showing in equation 1, in terms of the Krauss operators, really enforces the form in equation 2 of the channel. So this is why when I say you have effective depolarizing channels, this is sort of mathematically what's going on there. Right. Yeah, so that's RB twirling. People have come up with all sorts of different perspectives on this. Representation theory is a very common way of analyzing this. And people have also extended this to cases where, for example, the gates you're using to randomize also have errors and so on. Right. Okay, so that's the background on randomized benchmarking. So this has been around for a while. Specifically, what we are interested in is something called fully randomized benchmarking, which I'm going to introduce now. See some loads, sorry. Okay, so in a typical randomized benchmarking experimental implementation, these random sequences of Cliffords that I'm talking about, in practice, you just draw them and then repeat them many times. So you draw a random sequence, you input this into whatever control system that you have for the experiment, and then you run that a bunch of times and collect statistics about it. So the reason people do this in practice is really just that it's easier to do it this way. And in fact, it's very costly in most experiments to actually load in a random sequence into the control system and then run it. So it's comparatively much cheaper for them to just repeat a sequence many times and not worry about drawing new random sequences. So in fully randomized benchmarking, for every single trial you do, you draw a new random sequence and run that. So you don't repeat things at all. And that is really the difference between fully randomized and not. And so, like I said, this is sort of difficult for experiments. This is an added cost for them to implement fully randomized benchmarking. So one thing we've been very interested in is figuring out exactly what are the benefits of doing it fully randomized so that these experiments can decide whether it's worth it to them to go in this direction. So I'm going to spend the next few minutes talking about the benefits of fully randomized benchmarking as opposed to repeating sequences. The three main things that I'll talk about in more detail are going to be that you have reduced uncertainty in your inference of the step error, and in particular, predictable uncertainty. So this is actually very important in a lot of cases to know ahead of time what the uncertainty and the error bar you can expect is. And so having predictable uncertainty is pretty important. So there's that. There's also optimized experiment design. So if you have fully randomized benchmarking, then you can apply some really nice techniques from classical statistics to design an optimized experiment that also minimizes your error bar at the end of the day. And I'll talk about this. The third important thing is models of time-dependent errors. And this goes back to the non-Markovian behavior that I was talking about. So if you have a fully randomized experiment, it's fairly straightforward to start studying other models beyond the basic exponential decay and trying to do proper inference with those models. So I'll talk about these three things in some more detail. But really, to sum everything up, you really have a simpler analysis if you fully randomize with fewer assumptions. And this is something that we care about at NIST, irrespective of the other benefits. It's just having like a nice, clean inference procedure that assumes as little as possible. All right, so like I said, in the next few slides, I'll say some more about what these three benefits are. And so I wanted to start by talking about uncertainty in fully randomized benchmarking. And I think it's good to sort of make the case for doing everything you can to reduce the uncertainty in your experiment at the end of the day. And so here's a list of reasons why we at NIST really do care about minimizing uncertainty. One of those is that if you have fidelities close to 1 of your error channel, then you're pretty close to this statistical boundary at 1. In order to resolve that, you need to have your error bars be small enough that you can see the difference between your actual fidelity and then the maximum at 1. So if you can see this, then this makes inference a lot nicer. If you can't resolve the boundary, then you run into all sorts of tricky issues with confidence intervals and so on. And so if you have high quality gates, which we expect to have more and more of going forward, you're really going to start caring about minimizing the uncertainty as much as possible. So there's that. There's also rapid diagnostic and calibration. So this is something that comes up a lot of the time when we talk to experimentalists. In practice, they often have to recalibrate their gates. They're often done with some kind of laser pulses, and these things drift around all the time. So what they want to do is figure out what is the quality of the gate over time in as small of a time step as possible. The smaller your time step there, the more information you have about how that error is drifting, the more you can correct it, so on and so forth. So it's actually really important to get small confidence intervals as fast as possible, not just to save you time in the experiment, but so you can actually see some of these things which will come up. And there's also closely related is detecting drifts in the experiment. So things can be heating up over time, like the temperature of motional modes can be increasing. You want to be able to see this. In order to see this, you need to get your error bars as small as possible, as quickly as possible. So there's that. There's also distinguishing models, like I've been mentioning. If you want to search for evidence of non-exponential decay, the smaller your error bar on your step error, the better you can do in terms of distinguishing these things. And so this is really important. And then also just to make careful statistical claims, which is something we do a lot at NIST. If someone wants to claim they have the best gate ever in some platform, then you really want to make sure you're running a careful analysis that gives you a small error bar that you trust at the end of the day. Right, so this is why we care so much about uncertainty. In terms of fully randomized benchmarking, oh yeah, question.
A quick question about the calibration.
Yeah.
Rapid characterization. So that seems to assume that the experimentalists, like the time it takes for them to like load a U circuit is roughly commensurate with the time it takes for them to like run like a shot, but like typically
sure.
like, you can run like, hundreds or even thousands of shots, like once you plug the circuit in without any further input from the experimentalist, but like
That's right.
loading the circuit like does like take some compilation time. So
Yeah, exactly. And this is a big reason why people have typically not fully randomized. It's exactly what you're saying, is that once you load a circuit, it's easy to run it many times.
Right.
Yeah, so we do believe that as these platforms sort of mature, it'll be easier to load in a new sequence every time. And in particular, our collaborators did a bunch of work to try to like actually have this in their experiment. Yeah, so the fully randomized stuff that I'm talking about really does assume that you can do this. And also, yeah, when I'm talking about running rapid diagnostics and calibration, I am really assuming that you can load in fresh sequences basically anytime you run shots. Yeah, so I think you're absolutely right that in many experiments this is pretty tricky. But we hope that going forward, it'll get a lot easier. Yeah, and also as we start doing things like logical benchmarking, that should also help this. Yeah, but yeah, it's a really good point. Okay, right, so, oh yeah,
Like, out of curiosity, what then is this like loading process? Is this some hardware issue or is there some software difference?
oh,
They just need better FPGA?
yeah, it's a good question. So at least in the experiment that we collaborated with, loading things really means getting stuff onto their FPGA that generates their pulse sequences. So it's a microwave experiment. So the FPGA controls the microwave drive they use to actually perform the gates. So if you want to load everything in ahead of time, you have to get all this information about the random sequences onto the FPGA. And that's the thing that can be very time consuming, is loading like a pretty large amount of data onto this FPGA quickly. It's like not really designed for that. So actually I'll talk about this more, but in our experiment, they got around this by generating the sequences on the FPGA itself to avoid the loading. Yeah, thanks for the question. Right, so in terms of uncertainty of fully randomized benchmarking, one thing we wanted to do is to try to quantify the improvement in uncertainty you get if you fully randomize as compared to repeating sequences. And so this is one way we've been doing this. We've been looking at a particular sequence length n and looking at the estimator of the average success probability at that sequence length n. So if you study the variance of this estimator, which you can do, but some people have sort of done, you find that you can split it into two terms, which I've done here. So there's B fully randomized and then B extra. And this is just a convenient way to label the variance terms that you get. So the fully randomized one is always going to be there. And that's really just the binomial variance of taking binomial statistics of a success probability at some sequence length. So that's always present. B extra is what you get if you don't fully randomize. And what's interesting about B extra is that it actually depends on the error channel that you really have in the experiment. So I've been saying that the whole point of randomized benchmarking is to turn all the error channels into depolarizing channels. What's interesting about not fully randomizing is that the true channel affects the extra variance that you get in a pretty interesting way. And so this is how other things about the error channels can creep into a not fully randomized analysis. So specifically, when I say it depends on the true error model, for example, if you actually have depolarizing channels in the experiment, which you rarely do in practice, but if you actually have this, then B extra is 0, so there is no additional variance term. But we find that if you have unitary errors, and we studied this with an approximate unitary error model, then the B extra can be quite significant in cases where your errors are unitary and coherent and things like that. And so this was kind of our main motivation for studying variance here, is to see in practical experiments, does the extra variance term make a difference in your total error bar at the end of the day? And we find that it does, and I'll talk more about this in a bit.
One question.
Yeah.
Are you set a system size for randomized benchmarking?
Oh, yeah, good question. You're talking about the
Number of qubits.
Yeah. So the analysis that we've been doing holds for any number of qubits. But in order to actually generate these sequences and use them, you have to pick the number of qubits you have in the experiment. Yeah, so we really feel like that's something that the experimentalists tell us. They tell us how many qubits they have, and then other things about their experiment, and then we design the protocol for that.
Is there any dependence on the gain you get on the system size?
Oh, yeah. Yeah, there is. Yeah, it's, we have a formula that I didn't put up here that does have dependence on the system size. Yeah, but it's sort of hard to say whether it matters as the system size gets bigger. Like in the formula, there's a 1/d squared term, but it's sort of hard to see what to compare it to exactly. Yeah, so I think this is a good question and something to definitely think about going forward. We were mostly focused on the 1 and 2 qubit case, where it's definitely relevant. But yeah, for larger systems, it's something that we should definitely look into.
Do you use the dimension?
Yeah, to use the total Hilbert space dimension.
Okay.
Yeah. Great. Right. So the second benefit of fully randomized benchmarking that I want to say more about are the different models of fully randomized benchmarking that we're interested in. So to introduce these models, I wanted to talk about some notation. Right. So what really matters in randomized benchmarking is the success probability at sequence length n. So here that's denoted with p sub theta of n, where bold theta is just any list of parameters that you have statistically in your model of the experiment. So that's a very general statement. It's just that you have some p theta of n. And then in terms of some other constants, this is the basic model of randomized benchmarking, and this is the exponential decay that I was talking about. So you can see that there are two parameters. One is the span parameter, theta 0, that governs state preparation and measurement. And then theta 1 is the step error. And this is exponential decay based on the step error theta 1 as a function of sequence length n, in a way that's sort of offset by the state preparation and measurement error. So this is kind of the basic model of randomized benchmarking that everyone uses. And it's really just a single exponential decay. So I'm putting this up here in order to talk about how we've been generalizing it. And one way we like to generalize it is in terms of something that we call the moments model. So the way to motivate this is to consider step errors, theta 1, drawn from some distribution, which is left arbitrary here. That distribution is sigma. So if you do this, then in order to calculate the success probability as a function of sequence length, you can really just substitute in to the previous equation. But now instead of just the constant step error theta 1, you allow it to be drawn from a distribution at the beginning of each trial. So that's like, as you initialize the experiment, you imagine that you just get handed some value of theta 1. That's what you have for that sequence. Then when you start over, you draw a new value of theta 1. And then this can come from basically any kind of distribution. So this is a plausible error model for things that actually happen in experiments. When you think of this as kind of slow drift. Yeah.
Oh, sorry, what was the previous basic model? How's it different?
Yeah, thanks.
Sorry,
Yeah.
oh, okay, okay.
Right, so we really are using the basic model,
Right.
but then we're allowing theta 1 to kind of fluctuate trial to trial,
Oh, okay.
being drawn from an experiment. Yeah, so I got this equation really comes from just plugging in for the previous one where the step error comes from the distribution. Yeah. Right, so like I said, this motivates the moments model that we consider a lot. One way this works is that you can parameterize this in terms of the moments of the distribution sigma. So in principle, it has like a second moment, third moment, and so on. What we do is we basically add more of the theta parameters, the statistical parameters, corresponding to each of the moments of the distribution. So concretely for theta 2, that is like the second mean subtracted moment of whatever distribution you have for your errors. And then you just go on adding parameters as needed by considering higher and higher moments of sigma. So what is especially interesting about doing this, and this is really part of our motivation for considering this model, is that we find that this is universal if you have enough of these moment parameters and you don't worry about putting any restrictions on them. For example, you don't worry about the fact that they had to come from an actual distribution. So if you don't worry about that and you add enough parameters, you can basically capture any kind of functional form of peak data of n, which is a pretty interesting thing because it means there's sort of no point in trying to search for other models beyond this one. In principle, like if you add enough parameters to this one, you can always capture whatever behavior you have. And this is really what motivates us to think about things this way. So like I've been saying, this allows you to capture non-Markovian errors. So if you have some kind of non-Markovianity, this just shows up as some more complicated form of piece of data of n, which you can detect using the moments model. So two examples that we think about a lot are slow drift in the experiments over time and also fast drift. Any question?
Yeah, no, so I was wondering about the non-Markovianity. So
Yeah.
does it intuitively, it looks like you're drawing from a distribution independently for each step. Is that not the case in the Formula 5?
That is indeed the case. Yeah.
So how are you incorporating, oh, sorry, non-Markovian errors.
Yeah.
But so how you, if it's the same distribution for each step, how are you incorporating the non-Markovianity then?
Right, exactly. Yeah, so that is a sort of Markovian flavor of model. It's technically non-Markovian in the sense that in a true Markovian situation, you have the same error channel for every gate all the time, no matter what. So here, the error depends on what you drew. So there's kind of a memory effect during the sequence. Like it's constant throughout the sequence, then you draw a new one for the next sequence, then that's constant, then you draw a new one. So technically, this is non-Markovian, although it's a sort of very small, intuitively small amount of non-Markovianity. Right, so what's interesting is that the universality thing I'm talking about means that for any, in principle, arbitrarily complicated non-Markovian model that you actually have in the experiment, it's just going to look like this for some values of the moments parameters. Yeah, so it's like instead of going and hunting for all these different really complicated things you could have, what you can do is just use the moments model, get values for the parameters, and that's, in some sense, that's the best you can do. Like you can't really distinguish this from some really complicated non-Markovian thing. Right, yeah, so thanks, that's it's a really good thing to point out, and this is why we really think about this model.
So I mean, the quick follow-up, does this assumes a kind of stationarity, like there isn't a particular reference that you're like picking out, like
Right.
maybe in reference to like slow drift or like unitary angles, that kind of.
Right, exactly. So in terms of slow versus fast drift, we're really comparing to this time it takes to run the sequence. So for slow drift over time, that feels a lot like drawing the error from a distribution for every shot. Fast drift is like the errors kind of get worse and worse and worse as you're running the sequence. Yeah, so that's like the time reference we have there. We're interested in, for example, distinguishing these kinds of things to the extent possible using this kind of moments model. Yeah, thanks. Right, so in practice, to use this, you really have to truncate the number of moments because in practice, you can't just grow this to infinity. So really what you do is you cap this at something reasonable, and we cap it at 4 for the demonstrations we're working with. And then you just look for any evidence that you need these extra moment parameters to describe what you have. So it's sort of like expanding slowly from the Markovian case and introducing the possibility of non-Markovian stuff.
Like because if I'm truncating at second moments, if I'm understanding correctly, there's some kind of Gaussian distribution, but
Right.
sometimes if we truncate at higher order, like what ends up happening like with only a finite number of like non-Gaussian moments, like that doesn't really correspond to a valid probability distribution. Like
Right.
will that lead to any issue here? Like when you're trying to reconstruct like some kind of physical error model?
Exactly, yes, that's a really good point. So this is why I was talking about it's only universal if you remove those restrictions. Yeah, so like you're saying, if it really is coming from a distribution, there are restrictions on the moments. But if you remove that, then you don't worry about it. And then this is in fact one way that we hope to eventually distinguish errors actually coming from a distribution versus errors that are drifting, is via the exact constraints you're talking about. Yeah. Right. Great. Yeah, so that's it about the models of benchmarking. We'll talk about it in a few minutes in the context of the experiment. But the third thing I wanted to say a few words about is optimized experiment design. Like I mentioned, this is one of the benefits of fully randomized benchmarking. And so the way optimized experiment design works is that your goal is to maximize information about the step error or the parameter of interest under the constraint that you have just some amount of time to run this experiment for. And this is one way to frame the question of what's the most efficient way to get information about the step error. So that's kind of the way to frame the optimization. In detail, what we did is we put in a time cost for each sequence length based on just what they told us the time cost was in the experiment. So basically the choices you have for running the experiment is the choice of which sequence lengths do you pick and how many times do you run each one. Each of those has some cost. You put all of that together into an optimization, which is indeed convex, which is very nice. And you do this to design the experiment that you want to run. The way we think about this in terms of constructing optimal linear estimators of the step error in a linearized model, we like to think about it this way because these linear estimators are quite useful for other things. But this is indeed exactly equivalent to optimizing for Fisher information in this multi-parameter model. And so if you want to think about it that way, that works too. So what's nice is that this technique for optimizing the experiment design works for basically any statistical model that you might be interested in. And we take advantage of that by running this optimization for different moments models, like the ones we were just talking about. And so we'll talk about the benefits of this in a bit. Right, so those are really, in my mind, the three main advantages of fully randomized benchmarking. So in the remaining time, I'll talk about the very recent implementation in an experiment that was run at NIST in Boulder by our collaborators in the ion storage group. So they have a trapped ion experiment. Right now they're using magnesium. What they did is that they implemented single qubit randomized benchmarking by constructing a 2 design where each step in your Clifford steps consists of 2 pi/2 pulses. And they control the phase of the pi/2 pulses in order to generate all the Clifford operations that you need on a single qubit. So in terms of fully randomizing, what they did is they actually generated the sequences on the FPGA, like I mentioned before, which means that they have a system on their actual control hardware that generates random sequences, calculates the stabilizers, and propagates them through the sequence to determine what the expected outcome is. And this is all done on the fly in a really nice way. And this is how they avoid the issue of trying to load in random sequences and so on. So they did a lot of really nice work to get this set up. Once they had it set up, we wanted to design this kind of experiment that showcases the benefits of fully randomizing. So we thought about this. What we came up with is shown in this table. So we asked them to run 3 experiments where we modified the randomization and also the experiment design. So the 2 options for randomization are you can either have repeated sequences like you normally do in randomized benchmarking, or you can fully randomize the experiment. So in experiment 1, we had the repeated sequences. In 2 and 3, we fully randomized. So the difference between 2 and 3 is that in experiment 2 and experiment 1, we used a uniform experiment design where you just draw sequence lengths uniformly over some range. This is a very common thing in a lot of randomized benchmarking experiments. So this is what we wanted to compare to. So in experiment 3, we ran the optimization procedure that I was just talking about in order to design the experiment. In order to make a fair comparison, what we did is we constrained the total time for all of these 3 things to be the same. And that total time came out to about 53 minutes with actual experimental runtime. So in terms of this experiment, the step error that we expected ahead of time was about 2 × 10⁻⁵. The state prep and measurement error is 3 × 10⁻². So we are indeed in this regime where the state preparation errors are pretty large. So that makes randomized benchmarking a good tool. In terms of designing the experiments, our collaborators just measured how long it took to do various things. And they told us that each Clifford step takes about 2 × 10⁻⁵ seconds. The state preparation and measurement is slower at about 10⁻³ seconds. So we actually just took all that into account in the optimization for that 3rd experiment. Right, so that's how we designed this. I'm just going to show the results in the next few slides and then talk about it. So this is what the results of a randomized benchmarking experiment looks like. Here I'm comparing experiment 1 and experiment 2. You can see the individual points are for each sequence length, which we took uniformly in the range from 1 to about 50,000. That's 1 over the anticipated step error. So each point corresponds to a choice of sequence length. The height of the points is the inferred success probability at that sequence length. And then the error bar is the empirical standard error of that, so how much it's fluctuating over the different trials. And what's shown there is the fit to the basic model. And we fit to the basic model here because this one is intended to mimic kind of the standard randomized benchmarking that people are always running. And so this is intended to be compared to the second experiment, which has the exact same experiment design. But the only difference is that instead of repeating sequences on purpose, we fully randomized it. And so you can already see that the error bars on the individual points are getting a bit smaller, which is a nice thing to see. And we analyzed this according to both the basic model of a single exponential decay and also the moments model that we were just talking about. What's interesting here is that you can't really by eye distinguish these two models. Right, so that's experiments 1 and 2. We already start seeing smaller uncertainty at each length. Experiment 3 is the optimized, fully randomized experiment. So in the optimized experiment design, you can see that there were 4 sequence lengths chosen. And then different numbers of trials were run at each sequence length. So the error bars on these first 2 sequences are actually very small. That lets you see how many trials were actually taken at those points, and it was quite a lot. So the error bars later on start to get a bit bigger because the optimization said don't spend so much time running experiments at those sequence lengths. What's interesting here is that when we fit to both the basic model and the moments model, we start to see an actual difference between them, which we interpret as some non-exponential decay behavior. I'll talk about this in a minute. Right, so these are really the results that we have. Like I said before, we're interested in confidence intervals, in particular the size of confidence intervals. So the way we sort of get at this is by bootstrapping. So statistical bootstrapping is a way to generate confidence intervals from a data set. It involves resampling from your data intuitively to see how much the total number you get fluctuates as you resample. And so intuitively, the width of these histograms tells you the uncertainty in the step area that you were trying to infer. So this is all set up in a table for comparison purposes, basically. So the 3 experiments are in the 3 rows. The row at the bottom is the optimized, fully randomized case, whereas the row at the top is what you would expect for a sort of standard randomized benchmarking experiment, the way it's typically run. The 2 columns are the 2 different models that we analyzed. So the left side is for the basic model. The right side is for the moments model that we were discussing previously. So what's important here is that looking at just the basic model for a second, this is one way to see what the benefit is of fully randomizing and then of optimizing the experiment design. So we see that the confidence interval you get shrinks as you do both these things, which we think is a nice demonstration of the benefits here. So the actual improvement is that in the optimized, fully randomized case, the error bar there in the experiment is 4 times smaller than the error bar you get doing it sort of the standard way. So shrinking the error bar by a factor of 4 means that you would have to run the original experiment 16 times longer in order to get that corresponding error bar, which is like a pretty serious improvement in terms of total time. Something we hope our experimental colleagues are going to be pretty happy about. Right, so there's that, the factor of 4. It's actually even more pronounced for analyzing according to the moments model, which we think is important as experiments start to look for non-Markovian behavior. We really hope that they will be analyzing according to the moments model. Here, if you don't optimize the design of the experiment, you have a pretty large error bar. But if you do optimize the experiment design, then your error bar is really not that much worse than it is just analyzing according to the basic model. So we think if you kind of go through this fully randomized, optimized procedure, you can get error bars that are basically as small as you really wanted, but you can also include the possibility of non-exponential decay, meaning non-Markovian behavior. Yeah, without much of a hit to your total uncertainty. Right, so there's that. The last thing for this experiment is the actual numerical comparison between the basic model and the general model. The way we got this is we did a bootstrapped likelihood ratio test. What this means is that you assume that the basic model is true, resample from your data, and then see how it compares to a more general model. So if you find that a more general model does a better job of explaining your data, meaning the likelihood is pretty high, then you can start to do things like reject the basic model and say that it doesn't describe your data very well. So the way we do this is we generate this bootstrap histogram, and then look at where the actual likelihood ratio statistic that we observed in the experiment falls. So the farther it falls out in the tail, the more confident we are that we can reject the basic model and say that the general model is a better fit. So here we just ran the numbers, we got 6%, which can be interpreted as a p-value. So it's like with p-value of 6%, we reject the basic model and say that the more general model is a better fit. So this is how we really think about evidence of non-Markovian behavior in the experiment. Right. So the last thing I'll bring up is that we did this again, actually at the same time as the previous experiment, but with intentionally introduced coherent error. And the reason is we were really not sure ahead of time what to expect in terms of the improvement we're going to see. We were pretty convinced that we would see a big improvement for intentional coherent errors. We also wanted to show this. So to do this, we designed a very similar comparison, except now the step error is a lot bigger. That's 5 times 10 to the minus 4, because they actually just intentionally over-rotated their Clifford operations on the single qubit on purpose, basically. So here are the results from this comparison with intentionally introduced errors. Here, sort of as we expected, when you compare the standard case to the fully randomized case, the error bars shrink even more substantially here. And so you can see that you're getting much better signal to noise on these individual points. Because the step error is now bigger, the sequence lengths are smaller. So instead of 50,000, we only went out to 2,000 for this. Right, so there's that. Here in the optimized fully randomized case, the optimal experiment design actually looks quite similar. There are 2 small sequence lengths with a lot of emphasis given to those. What's interesting here is that you don't visually see much difference between the basic model and the moments model. The interpretation for this is that they intentionally introduced these coherent errors, which are pretty large compared to whatever non-Markovianity down at 10 to the minus 5 we were just thinking about. So you don't really expect to see any deviation here, and we find a nice confirmation of that, basically. Right, so here are the same bootstrap histogram plots. Again, we see a nice benefit from optimized fully randomizing, and then a correspondingly larger benefits if you actually analyze according to the moments model, which is pretty much what we expected, and it's nice to see this actually confirmed. And then here is the same empirical likelihood ratio test. So like I was saying, how far you are in the tail determines how much you can reject the basic model. Here at 50%, you don't really see much evidence for rejection, which tracks well with what I was saying before in terms of not expecting to see any kind of drifts at the 10 to the minus 4 level. Right. So I guess all that is to say that the experimental demonstration you did seems to have worked pretty much as hoped. So I've been talking a lot about the benefits of fully randomized benchmarking. Those include reduced uncertainty, the ability to optimize the experiment design, and the ability to look for non-Markovian errors. What's really nice here is that it works really for any randomized benchmarking model or variants, and there are a lot of different variants of randomized benchmarking that are out there. We hope they could also see benefits from fully randomizing. Right, so there's that. Then the experimental implementation, we were able to demonstrate that you get reduced uncertainty for optimized fully randomized benchmarking. And we also see evidence of non-Markovian errors, which is something that we're pretty excited about. So that's the experiments, and that's all I have for today. So thanks for listening.
Nice. So I just want to ask about the normal Boolean errors.
Sure.
So you can show that there's evidence of non-coding errors, but is there a way of like quantifying how much of everything is this given by the like percentage up there, 6%, and I actually think that's like a grade of how
Right,
it's not Markovian.
that's right. I mean, this is not a great answer because it's sort of hard to know what to do with this number. I think of 6% as saying something about our confidence that there is some kind of non-Markovian happening. If you want to figure out what exactly is going on, you're gonna have to do a bit more work to look at specific models that we think are experimentally relevant and kind of search for it there.
But like just kind of beyond that, I just want to know like what's not like percentage of noise or something, but like some kind of quantify about how large the non-Markovian effects are. Is that any way of getting from this?
Yeah, I feel like this is a reasonable proxy for that. But I mean, there are always details when you try to interpret these kind of statistics. Yeah. So really, to be very careful, you would say that, like I said, this is just how confident we are that there is some. But intuitively, that's probably very close to what you're saying, which is like, what is the size of the actual non-Markovian entity? Yeah. Thanks.
This be like, tell us anything about what kind of non-Markovian error, like there is in
Right.
the system, like what
Yeah.
attempt to use different.
Yeah, so that's a very good question. The short answer is really not yet. Like I said, you can try to get a sense of what the non-Markovian error is by looking at whether the moments parameters that you infer could actually come from a distribution. The thing is, you need a lot of data to try to sort these things out. And in this experiment, we didn't feel like we had enough confidence to either say one way or the other, whether we could reject like the fact that the moments parameters actually come from a distribution. Yeah, so that's something we're definitely interested in going forward. The easiest way to achieve that is just to take a bunch more data, really try to nail down those parameters so you can check the constraints. Yeah, but in this experiment, we don't feel like we can really say anything. Yeah, thanks.
I had a question about the moments model. Sure. Can you see a bit more? What is the functional form of sigma when you specify the first 4 moments?
Oh, right. So sigma is really sort of abstract here. And what we do is we just basically take equation 5 and then binomial expand it so that you are writing it in terms of things that look exactly like the moments.
Oh,
yeah. And then we just truncate those at a certain level. So we're never working with sigma directly. It's like sigma motivates the construction of a model that has theta 0, theta 1, theta 2, and theta 3.
Oh, it's like you take sigma and expand it in terms of the moments.
Yes, yeah, take sigma and expand this. Use the model that it gives you.
Okay.
Doing that, yeah, thanks.
And like, just for reference, so if sigma were to be a delta function, then this would be the case of purely Markovian.
Yes, and there you would find that all the higher moments are 0. Yeah, thanks.
If not, then let's thank the speaker again, and here's lunch, thanks to Cody and RQS. Sure.